All right, welcome in. This is kind of a studying session I'm doing on topology. Just as a little background, don't expect this video to be anywhere along the lines of me teaching because I myself am trying to learn. I am working out of Munkres' Topology second edition. That is a very classical text in mathematics. I'm going to be trying to really talk through my thought process, work problems here and there, depending on the section I'm in, because not every section in the book actually has problems in it. But once again, a little disclaimer here that I am not an expert in topology. I am just trying to learn it, and this is really just going to be me kind of talking through my thought process and trying to understand the concepts that are presented in this book. So with that being said, I guess I'll get underway here. I'm starting in chapter 2 of the book, which is topological spaces and continuous functions. Chapter 1 is over set theory and logic. I came into this course with a pretty solid foundation of analysis to begin with. If you're somebody who may not have a strong analytical background or may need a refresher on set theory, then chapter 1 would be like a really good place to start. But for me personally, I'm just going to start in chapter 2. The first chapter or so of topological spaces in section 12 is really just kind of touching on just a brief history of topology, and by brief I mean very brief, just kind of throwing out a few names out there like Hausdorff to, I guess, set the stage as to why we're making some definitions pretty rigorous. But right off the bat, it seems like we're kicking off into the definition of a topology. So a topology on a set X is a collection. Let's go ahead and and I'm going to be typing in kind of like a mixture of LaTeX in this Word document. Is a collection T of subsets of X having the following properties. So it seems like 1, the empty set and X are in that collection T. So we're going to empty set, and this is the thing that I'm not a big fan of Word, but it just kind of like works out for me here. It's just easier to deal with some of the problems of having to hit enter for LaTeX to actually compile in here. Somebody might have a better way. I just haven't bothered to look it up, to be completely honest. So the empty set and X have to be contained in that collection. So to me, this is reading that you have to have the empty set. So out of all the collections, I guess I should start with thinking through collection. So if you're not super familiar, we kind of have, you could think about it as layers, where we have points, then we have sets, and we have collections. Oh, that was pretty ugly, I'm sorry. So we have points, sets, and collections. Now, keep in mind, the arrows may not be like the best representation of this, but this is kind of like how I'm thinking about it at first. So points comprise sets, and a collection, a sets, is what makes up a collection, which is denoted by cursive letters. So whenever we see these cursive capital letters, that means we're talking about a collection. Now, what might a collection look like? Let's say I have a set X, which is comprised of points A, B, and C. So something just like super simple for us to look at here. So what we do is we create a collection T. And I actually might go ahead and just make some of this in here, but I'm going to jump the gun a little bit because I'll revisit it here in a second, to where I'm just going to say I have that, and then let's just say a singleton in here of A. And I just threw out the word singleton. Singleton is just like a single point. Um, Once again, feel free to correct me, but I've always just taken it as singletons, like single point. Um, this would actually form a topology, but we actually haven't worked fully through that definition just quite yet. But this is kind of the visualization of what a collection is. So we would say that X is an element of this collection. So a set is an element of the collection, if that makes sense. So jumping back over, we still have two more points that we have to hit on. The union of the elements of any subcollection of T T is in T. And then I'll touch on that here in a second as well. But then we also have one more point of the intersection of the elements of any finite subcollection of T. See, I wish I could just hit enter and it just do it instead of me having to whatever. Of T is in T. Okay, and then just to kind of like follow, kind of round out the definition, I should say, is that a set X for which a topology, in this case we call T, topology T has been specified, is called a topological space. Okay, so this is our formal definition of a topology, and this is where we're kind of be jumping off in for the rest of the class. For I guess course, I should say. I kind of touched on this first point. This first point's like relatively trivial. You just need to make sure that the empty set and the entire set are contained in your subcollection. Are within your collection of sets, not subcollection. Not there yet. Now, the union of the elements of any. So this is the word that kind of like sticks out to me here. Of any subcollection of T is in T. So the way I'm reading any here is you have to keep in mind that we have infinite sets, right? So in a finite case, this is very easy to check for. But what if we have an infinite set, for example? And so when I see the word any, that means the union of all subcollections have to lie within T in of itself. So if I hop back over to this guy right here, I'm actually going to erase this part. Sorry about that. And I'm just going to move it. So I'm going to keep it on there just for the sake of having it, but I'll just say X is an element of T. So if we have this T right here, the union of anything here has to lie back inside the set. So if I were to take the union of the empty set and X, well, that's equal to the entire set X, which in this case lies within my collection. If I take the union of the empty set and A, then that just gives me A, which is also inside of my collection. If I were to take the union of X and A, then that just gives me X, which is back inside. And then if I were to take the union of all of these together, that just gives me back my entire collection. So once again, I land back inside. So this is a finite case, for example, and this does check that box. So now if I hop back over here, a set X for, sorry, the intersection of the elements of any finite subcollection of T is in T. So this part, once again, kind of like sticks out to me now that I'm seeing the word finite being thrown around in here. Finite to me, that like obviously finite, like we can't have infinite numbers of intersections here. So there's some number of intersections that we would stop at, and those intersections all have to go inside of our set T. Sorry, not set T, our collection T. Correct myself there. So if I were to take the intersection of any of these, it should land back inside of this collection. So if I take the intersection of the empty set and the entire set, well, obviously they have nothing in common, so that just gives me back the empty set. If I take the intersection of X and A, then that gives me A, which is back inside my set. If I were to take the intersection of A and the empty set, then that gives me the empty set, which is back inside of my collection. Sorry if I keep mixing around words on set and collection. I'm still trying to like get it pretty solidified in my head. Like sometimes I may say set, but like I'm staring at this T over here and I'm thinking collection, but I'm just saying set. I apologize in advance. And then if I were to take the intersection of all three of these, then that just gives me back the empty set. So that lies back inside my collection. So in this instance, this actually checks all the boxes for a topological space. So this forms a topological space. Now, the other point that kind of sticks out to me about this definition is that this is just a set, and we have a collection of subsets of X. And there's multiple ways that we can form those. So like, let me call that T1. I can create like a T2 here. And I know me saying like T2 may not be the best notation right now, just because there is already a concept of like T1 and T2 in topology, if I'm not mistaken. But it is with just like a regular capital T. So just bear with me here as I'm kind of like grinding through this notation. So for example, I can create something like the empty set X, and instead of A, I can create B in this instance. And for the exact same reasons as the one above, this actually checks the boxes for a topological space as well. So what I'm gathering here is that one set can have a multitude of topological spaces associated with it. Now, they all could be slightly different. They could all be they could all act the same, I guess. In quotation marks, act the same. I'm actually not entirely sure on that just quite yet. But we can kind of keep moving forward in the notes here. But like I said, the big takeaway for me here is we have a definition, for what is a topology, right? And then we also come away with the understanding of the fact that like one set can have multiple topologies on it, and I think that is a big portion of chapter 2 here, is talking about how like all the different topologies you can form on sets and the special characteristics they might have. So here is another portion that he does not have in this book listed as a definition, but I think is pretty close to one, honestly. I won't label it definition because the book doesn't, but I think it's like pretty straight. It definitely falls under the idea of a definition. So if X is a topological space with topology T, we say that a subset Q of X is an open set, which is a big deal. If you've taken analysis before, you'll understand that open and closed is a very big deal in these topics. It's an open set of X if U belongs to the collection T. Okay, so right here we're jumping into the idea of open sets. So something is open if a subset is open if it belongs to the collection. So let me jump back to this example over here. So a subset, let me think through this. So if X is a topological space with topology T, we say that a subset U of X is an open set if X of X if U belongs to the collection T. Okay, an open set of X. Okay, so we say that a subset U of X, so I'm tying it back to this guy right here, my T1. So let's say U is equal to just the singleton of A here. Is an open set of X if U belongs to the collection of T. So in this case, this would be an open set because U is a subset of X. That's a fact because, A is just in there. But U is an element. U is also an element of T, so therefore U is open. So U is open. Okay, so the idea here is that an element of your topological space, a subcollection of X, a subset, not subcollection, a subset of X is open if it belongs to if it is an element of your topological space. Okay, let me say that one more time for myself. A subset of X, so a subset of your set, is an open set if it is an element of your topological space. Okay. And once again, openness is like a pretty big deal here. The next portion of this is jumping into some examples of topological spaces. I'll hop back over and look at kind of the other examples. He gives like a pretty good visual where we draw out like 3 dots, like A, B, and C. So he's still he's using this X equals ABC here. I'm just going to draw out one of them just so we can kind of like get a look at it. So let's say I draw some circles around like this. Okay, so what this translates to, and let's just call this T3. So we're under the assumption that the empty set is in here because you can't really visualize an empty set. So we're just going to assume the empty set is in here. Then we have X, which is the big circle on the outside. We have a collection of AB. So we have a collection of AB. Then we also have a collection of BC. And we also have a singleton of B. Okay, so tying this back into our definition of a topological space, so it checks off the first point. The empty set and X and the entire set are contained inside of this collection. So check 1. Next we need to check for unions. So do the unions of these fall back inside of this collection, right? So these two are pretty trivial over here for the unions. So I'm just going to be focusing on these guys over here. So this first one, AB union BC, that just gives me ABC, which is my entire space X. So we're good there. AB and B just gives me AB. BC and B just gives me BC. So it looks like we check off our second box over here. The next one that we need to check off is the intersections one. So once again, X and empty set are fairly trivial. Okay, so if I take my space and intersect with AB, I get AB. Same with BC and B. Now if I intersect AB with BC, that gives me B, which is inside the set. If I intersect AB and B, that's B. BC and B, that's B. Okay, so this checks out. This is a topological space by definition. So we were able to construct that. Now I want to talk about openness again, just because I'm still kind of wrapping my head around like how we define open sets here. So AB, so U is a subset. So like let's call this U, which is a subset of X. So this is open in this topological space. Now, if I were to take now just as an example of like something that would not be considered an open set in here. So like let's say I have V, which is a subset of X, where V is just equal to the singleton point of C. This would not be, I guess I should avoid using X since I'm writing it out so much. So this would be not open in T3. So I think I do need to specify here that this very well could be an open set, but in this particular construction, it is not an open set. So open sets have to lie inside of the collection for the topology that I define on it. So I think this is another pretty key point that I'm kind of drawing from this first part, is that something may be open in one topology and it may not be open in another topology on the same set. So this ties back to my thinking and logic of the idea that different topologies yield different one set can yield different topologies, and so those different topologies can have different concepts of open and closed behind them. So I think that's a very key point that I need to take away from here. Let's give it a quick example. Let's kind of use the same set, ABC, to give you a non-example. So I'm going to draw these dots again. Just take it that this is A, B, and C. Sorry about the handwriting here. Let's go ahead and circle it like this. So I don't really want to call this. No, I can call it this. I'll just call it T4. We're going to check to see if this is a topology. So once again, we're just going to auto-assume that the empty set is in there because I can't really visualize nothing. Then we have a singleton of A, and then we have a singleton of B. Okay, so checks the first box. This guy and this guy are inside of my collection, so we're all good there. Now we need to check for unions. Well, if I take the union of A and B, which are elements of T4, which are elements of T4, well, that's equal to the set of A comma B, which is not an element of T4. Therefore, T4 is not a topological space. And I'm just going to say top SP for topological space, just for some shorthand here. Now, just because something is not a topological space doesn't mean it's a collection. Going back to the definition of a collection is just it's a collection of sets. So this is still a collection. It's just not a topological space because it didn't meet our definition of a topological space. Okay, so jumping into the next portion, I believe he brings up discrete and trivial topologies. So the discrete topology is the collection of all subsets of X. Yep, so the discrete topology is the collection of all possible subsets of X. It's basically as deep as bulky as you can make a topology. Maybe not bulky is maybe not the right word because we're going to be talking about finer and coarser here in just a second, but the trivial topology is the collection of just the empty set Okay, so the trivial topology is the collection of just the empty set and the set itself. I think that's pretty straightforward to see, to be completely honest. You know, it passes the eye test of like all the three boxes we have to check because clearly satisfies one because they're the only two in there. The union of this and this, well, that's just all of X, which is inside of it, and the intersection is just the empty set, so checks all the boxes, which I guess is why they call it the trivial topology, because it's super easy. Discrete topology, the collection of all subsets of X. So what might the discrete topology look like for this guy up here? So let me write out So this is the discrete topology on my set X. So I'll just give it a T sub D for now for discrete. I don't think I'm going to run into any complaints on that one. So obviously we have to have this guy and this guy in here. We need to contain all of the singletons. So in this case, that's A, B, and C. And then we need to start going through the combos. So we need A and B. And then we need B and C. And then we need A and C. And then ABC is just X, so we can close it out here. So this forms the discrete topology on X. We contain all possible subsets of X in this one. So we have all of our singletons, then we have the combos, and then the entire set. Just a quick little double check that this does form a topology on X. The empty set and X are inside of my collection, so that checks off our first box. Let's do a quick check on the unions. Once again, it's pretty trivial for the empty set and the entire set on the union, so I'm just going to be focusing on these guys. If I take a singleton and union it with a singleton, so AB union gives me this AB, AC gives me AC, BC gives me BC. If I were to take a singleton with these doubles over here, well, AB and A just gives me AB, this just gives me AB, this gives me the entire set, and it's kind of vice versa for these two over here. Now if I were to go ahead and union these guys over here, well, AB and BC, that's just the entire set. AB and AC, well, once again, just the entire set. BC, AC, well, once again, that's just the entire set. So it passes the second condition for a topological space. And then lastly, we have the intersections. We'll intersect AB, empty. The intersection of any of these singletons is actually going to be the empty set, so that's pretty easy to check. The intersection of these singletons with any of these guys over here just gives you back this singleton point inside of your set, and the intersection of these guys over here just lands you back at a singleton. So checks all three boxes, so we can happily say that this does form a topology on X, and specifically this forms the discrete topology because I just have all of the all of the subsets of X in here. There is another example that Munkres gives, and sorry if I'm like mispronouncing Munkres. I'm pretty sure that's how you say it, but I'm not like 1000% sure, to be completely honest. We're delving more into the abstract realm with this one. So we are going to be defining the finite complement topology. I believe I've also seen this written as the cofinite topology specifically. We have, okay, so let me just kind of write it out. X be a set, and let, oh my gosh, this is okay, let me, okay, so let's just call it T. It's really T sub f, but I don't really feel like going that ham. I'll write it out on the whiteboard side and then just kind of pull it over. But be the collection of all subsets U of X such that X. So this is set subtraction. So set difference. You will, you might also commonly see it written like this. I've just always seen it written like this personally, so that's just what I'm going to be kind of using here, but they're both the same. It's fine to use either. Either is finite is all of X. Okay, then we say then and T is a topology on X called the, and this is where we get into our definition here, the finite complement topology. Okay, and you might also see it written as cofinite topology. I believe that's like another relatively common way to see it. For, you know, obviously this is coming from the book, so, and it's part of his example, so it does form a topology, but I do think it is a good exercise to kind of like see why this is a topology. The first thing that I'll do here is I'll just write cofinite because that's easier to write. So cofinite topology. I'm not going to say on X because that might, I don't want you to get confused that I'm referring to this guy up here because the cofinite topology can be applied to this set X, but I don't think that was really the intent of the cofinite topology. To me, the cofinite topology is geared more towards like what an infinite set would be off the top of my mind. Potentially. Once again, not like 100% sure. I'm still trying to learn this stuff. So the first thing we need to check is we need to check that the empty set and X are indeed elements of my topological space, which I'll just call CF for cofinite topology. I'll write that up here as well. So the first thing we know is we know that X less X does land us with the empty set. So we know that this is finite. The empty set is finite. Nothing is finite. So I'll write that this is finite. So it does belong to TCF, my collection of cofinite. And then we also know that if I were to take the entire set and take away the empty set, that leaves me with the entire set, which, once again, by construction, we said that the cofinite topology is defined as either being finite or the entire space, which in this case is X. So that means it belongs to the cofinite topology, and therefore we have checked our first box over here. Now the next one is arbitrary unions. Let's go ahead and think about this. So the way I'm thinking about arbitrary unions here is that means I can have any subset that lies inside of that is an element of my collection, right? So let's say let U sub alpha belong to my collection, right? What I want to show is I want to show that the union, and this is the part where like bear with me, I'm going to try to make this as easy to read as possible. The union of U alpha is also in. So I'm saying pick a random subset, right? Pick a random subset that we're indexing with this alpha, right? So in this case of the discrete topology up here, this is just an example. I'm just kind of like pointing at it. Like this singleton of A would be like a U sub alpha, and this would also be a different U sub alpha, and this would be a different U sub alpha. So I'm just kind of generalizing what would exist inside of here with just a singular notation here. So we want to show that the union belongs in there. Now, if we were to compute, and these are the exact words that Munkres is using, is we compute. So if I were to do x less the union of my U alphas, then that's the same thing as the intersection of x less U alpha. Now what we know is that this must be finite. And that's because we are taking an arbitrary set and doing a subtraction with a finite set in this case. So we know that that's going to be finite, and the intersection of finite spaces is itself finite. So that means that this is going to go ahead and lie inside of my set. Now keep in mind that this right here, this is part of my original construction where I said that we're constructing this this collection. So like I guess maybe I should write it up here. Let's call it U sub alpha such that U is finite or X. Okay, so by construction of the cofinite topology, we're defining that it has to be constructed from this subtraction, right? So that's why I am subtracting this X from this union over here. Now, once again, this part over here, it may seem like we kind of gloss over it, but if you're familiar with your set theory at all, you should know that a set less a finite set will yield a finite set in this instance. The next portion we want to show, so let me put a check mark over here. The next portion we want to show is that the a finite intersection. Let us go ahead and create an index here. So I'm going to, like, let's say we have U1 all the way to UN in this instance. So I'm creating a finite, like an arbitrary finite collection over here. And let's say that they're non-empty. because if they're empty, it's just trivial at that point. Now we want to show that the intersection of these UNs belongs back inside of my collection. So once again, by our construction of how we built out this topological space, I would say my set X less the intersection. Now keep in mind that these are finite intersections, so I do need to create an index for this particular one. I did not need to create an index up here because it's for any union. So that could be the entire space, that can be a finite union, but that's why this one was left arbitrary. But this definition is specifically for finite intersections, so I do have to index it. So then I have u sub I. Well, this can actually be rewritten as the union, and this index also has to be, this union also has to be indexed because this intersection was originally indexed of x less that ui, right? Now, what we have here is, once again, this is finite. Because this guy over here has to be finite, right, by our construction up here, or all of x. But what we get over here is a finite union of finite sets, which in of itself is finite. So checks the box. So the cofinite topology does indeed form a topology on a set X. Now, something very interesting to note here is how we worked through this cofinite topology is we made it very abstract, right? So what I'm really saying here is that I could apply the cofinite topology to any set here. Any set can have the cofinite topology placed upon it. This is a topology that we can broadly use, right? The last one is a co-countable topology. It's very, very similar to the cofinite topology. I believe, I don't think there was a specific name that Munkres gave it, but I have seen it as co-countable pretty frequently. And we are letting TC just be the collection of all subsets U of X such that X less U is either countable or all of X. So I'm really just going to kind of like, do a little copy paste action over here, because this is the, what is this? I'm just going to say co-countable. The co-countable, I'm just going to ignore it. Maybe I'll just put a dash in between the two. Maybe that'll make it a little bit happier. Such that X is either finite, so that this is countable, or is all of X. Once again, this actually follows the exact same line of logic as we just used for the finite complement topology. Once again, we have countability in here, and we also have the entire set. We use pretty much this exact same logic over here, just replacing finite with countable, and replacing finite with countable, and it checks the exact same boxes. So really the proof for the cofinite topology really just follows the same proof of the co-countable topology. So once again, very important note that I'm kind of picking up here is that the co-countable topology can be used on any set X. So we can construct a co-countable topology on any set. It doesn't just have to be a specific little set like we had up here. Okay, so flipping back, the last thing that I believe this section, the last thing that this section touches on specifically is the idea of finer, coarser, and comparable. Okay, so just bear with me here for a second as I kind of like talk through typing this out. So suppose that, ooh boy. Could I be smart and just copy and paste this T, you know? I could, but I'm not. See, this is the thing. Is like if I exit out, like I have to hit enter in order for it to even just freaking register it, which is stupid. So suppose that T and T prime are two topologies on a given set X. If T is a subset, or I guess a subcollection of T prime, so I will say if, you know what, screw it, I'm just going to go ahead and do the old copy paste action. Slash subcollection. Ooh, what is it? What is that notation? Oh my gosh, I have it up here. Oh, sorry, latex. What is it? Subset. I think I just need to call it subset. I just inherently called it subcollection because that's what it is when I read it out loud, like with this format. We say that in this instance, we would say that T prime is finer than T. We say that it's finer than T. Okay, so we have two topologies, and this harkens back to the idea of like our original sets of like A, B, and C, that from one set we can yield multiple different topologies. So the way that I read this is that here, like, let me flip back to like an actual example here in this instance. So this T1, we already verified that this forms a topology, right? Well, T1, well, that's actually just a subset. Or here, actually, let me talk about T2, because T2 and T3 are just like right here next to each other. So T2, right? Well, T2 actually is properly contained inside of T3, right? Like I have the empty set X and B, empty set X and B. So what we would say is that T3 is finer. The analogy that Munkres gives is like little pebbles, and I think that's actually like a pretty good analogy. I've also seen the analogy of like coffee grounds, but the idea is that we are essentially taking something and making it finer, as in we're adding, like there's more things to look at, right? Like if I take a rock and then I smash it up, so like if I take a rock and then I take a hammer, sure, let's call this a hammer, just give it a little swinging action here, you know, and then I start getting like all these little pebbles. Well, the fact that like I haven't changed what all happened for this rock, right? Like it's still technically made up, like it's still made up of all the same parts. I just cut it up into a bunch of smaller pieces. And so that's the idea behind what finer is that you're taking something and you're just cutting it up into more pieces, so that you have a more intricate topological space per se. This also brings in the idea of coarser. So coarser is just the opposite of finer. So T3 is finer. So I would say that this is finer and that this is coarser. Yep. So this is kind of like the direction we talk about, finer and coarser. There's also the idea of strictly finer and strictly coarser, and that's if T prime properly contains T. in this case, it does properly contain it. But we just stick to the idea of finer and coarser. Now, what we do is we say that topological spaces are comparable. So let me flip back over here. So let's say we say that T is comparable with T prime if either this guy holds true or the other way around. Or the other way around. Yeah, there is a space there. Okay. So two topologies are comparable with one another if one is a subset of another. So in this particular instance, T2 and T3 we would say are comparable to one another, and that T3 is finer than T2 or T2 is coarser than T3. Munkres does make a small note in here stating some mathematicians would call this guy over here, larger, T3 to be larger because it's, if you were to just kind of like, count inside of here, it's larger. And you didn't see me, but I'm kind of putting quotes around count here because that's kind of like a loaded, a loaded thing to say, especially once we start talking about like infinite sets. But this is larger than what T2 is, and this would be smaller. Although I prefer finer and coarser personally. I think it makes more sense because this rock analogy over here just makes a lot of sense to me. But with that, that ends the first section. I know this is kind of like long, but once again, I'm just kind of like talking through my thought process here. Is like whenever I'm reading these definitions and I'm trying to like digest what the book is saying, like this is like what goes through my mind. Next section up is section 13, which touches over the basis for topology. It's a little longer, so hopefully I don't spend as much time, but we'll see. All right, thank you so much. Bye.